Find the real me. So let's go, seize the feeling. 'Cause you know it's time for the meaning. Now we show we're coming to win it. Find the real me. So let's go, seize the feeling. 'Cause you know it's time for the meaning. Now we show we're coming to win it.
In motion differential equation, our objectives of this video is first, for the viewers to enhance their problem-solving skills. And the second, to appreciate the significance of motion in actual world. Third, articulate the importance of motion, which is velocity and acceleration. And the fourth, to be able to fluently discuss the flow of pedagogy. So before we're going to present to you guys a short video presentation, let me give you a short historical background about the differential equation. So differential equation began with Leibniz, the Bernoulli brothers, and others from 1680s, not long after Newton's fractional equations. In the 1670s, the applications were made largely to geometry and mechanics. Isoperimetrical problems were exercises in optimization. So Leibniz is the one who founded the differential equation. So as time goes by, differential equation becomes more complex and it develops more equations and up to the point that they discover a new branch of differential equation, which is motion differential equation. So what is motion differential equation all about? So differential equation arose from the work of Isaac Newton of dynamics in 17th century, and the underlying mathematics ideas will be sketched here in the modern interpretation. So the differential equation of the body in motion is given by dt times dv equals to k times the quantity of 1 minus t, where k and t are constant.
Okay, class, our discussion for today is all about motion or motion differential equation. So I will be calling somebody in class to please answer my question. Does any of you know what is the first derivative of motion? Okay, Ms. Lero.
Velocity, sir.
Yes, that is correct. Can you please further expound your answer?
So the first derivation of motion using by graphical method is the first equation of motion can be derived using a velocity of time graph for a moving object with an initial velocity of u, final velocity of v, and an acceleration a. There are three methods used: algebraic method, derivation using graphical method, and derivation using calculus method. That's all, sir.
Okay, that's very good. So, okay, so all of your answers are correct, and you overpassed my expectation about you, so I am expecting more about you. So, you will now sit down. So, does any of you know the second derivative of motion?
Sir,
Okay, Miss Brunella.
acceleration.
Yes, that is correct. Can you please expound it for me?
Acceleration is the name we give to any process where the velocity changes. Since the velocity is a speed and acceleration, there are only two ways for you to accelerate: change your speed or change your time or change both. Represented by the equation, acceleration equals change in velocity over change in time squared.
Okay, that's correct. So, in respect to this, I will be asking somebody in our class to please discuss me what is motion. So, Cabreros, do you have any idea what is motion?
Yes, sir.
Can you please discuss it too?
Yes, sir.
The original equation of motion, usually identified as some physical law and applied to physical activities. It is used to set up an equation for a problem. So, solving the differential equation will lead to the general solution with arbitrary constants. So, the arbitrariness or corresponding to a common solutions. So, that's also.
Okay, Miss Cabreros, that's right. So, okay, this will be the problem that we will be solving. So, a boy, excuse me, 1.2 meter tall is walking directly away from the lamp at a rate of 0.9 meter per second. If the lamp is 6 meters above the ground, find the acceleration at which its shadow is lengthening. So, for us to efficiently understand this problem, I will be drawing an illustration for us to better understand this given problem. So, 6 meter represents the lamppost that is 6 meter above the ground, and 1.2 meter represents the boy. So, in this, after that we'll be letting any variable in a given scenario, so we'll be letting any variable. But since we are just being decentralized by this, by the variable x, so we'll be using x. So, after we assign their respective variables, we will be differentiating them. So the differentiation of x is just the derivative of x with respect to t. And since we use s here, because we're finding the acceleration at which his shadow is lengthening, so I use variable s. So the differentiation of variable s is just the derivative of s with respect to t. And since we have a given value or a constant value at a rate of 0.9 meter per second, in which the boy is walking directly away from the lamp. So this is his constant value. So it is 0.9 meter per second. Then the only trigonometric function that will satisfy this problem is the only trigonometric function that will satisfy or complement this problem or illustration is tangent theta. Why tangent theta? It's because the opposite and adjacent is given. So the only trigonometric function that will satisfy this is only tangent theta. So tangent TOA is opposite over adjacent. So our opposite here is 6 meter and x and s. So we will use 6 over x plus s. And tangent theta, on the other side of that illustration, it is also opposite and adjacent. So we will still also use tangent theta. So it is 1.2 over s. So for us to simplify this equation, we will use this. X plus s is equal to 1.2 s. It is the simplified version of this specific or particular equation. And after this, we will cross multiply them. So it's just 6s is equal to 1.2 times x is equal to 1.2x then 1.2 times s is just 1.2 s. But since they don't have the same variable, we cannot combine like terms. And the only coefficient and has a same variable is 6x. So we will be transposing 1.2s to 6s. So we will subtract it. So it will become 4.s is equal to 1.2x. And before anything else, we will derive these two variable. So I mean, we will be differentiating this two variable. So a differentiation of s is just 4.8, a derivative of s with respect to t, because we are talking about time. Then the differentiation of x is just dx over dt. Or, sorry class, my mistake. So it is wrong. It is a wrong terminology to use dx over dt, because the right terminology for this is the derivative of x with respect to t, or with respect to time. So 1.2, the derivative of x with respect to time. But since we're not done yet, but since we have a constant value 0.9 meter per second, we need to plug this 0.9 meter per second for us to come up with the right solution. So it will be like this. So after we plug in or substitute the constant value 0.9 meter per second, we will multiply it. So 1.2 times 0.9 is just 1.08 meter per second. And just bring it down to 4.8, the derivative of s with respect to t. But since we're trying to find the acceleration at which his shadow is lengthening. So we need to divide both sides by 4.8. Then cancel 4.8. D is that bring down the derivative of f with respect to t. So we will have an answer of 940 meter per second. And if we convert it into decimal, it is equal to 0.225 meter per second. So that is how to calculate the acceleration at which his shadow is lengthening. So does any one of you understand the flow or the process of the solution?
Yes, sir.
Okay, good. Now that I'm done solving this problem, I will be calling somebody in our class to solve the next problem. So, who is willing to volunteer in solving the next problem? Yes, sir. Please raise your hand. Okay, since that you are the next somebody that will solve this problem, can you please erase the writings on the board? Yes, sir. Okay, thank you very much. Okay, I will be writing in illustration for us to efficiently understand this particular problem. So this will be our illustration for this particular problem. So this will be our particular diagram in this particular problem. So Mr. Martinito, are you done solving this problem? Yes, sir. Melvin Martinito, you can now proceed in solving this problem. The board is all yours.
So by applying Pythagorean theorem, we will use this equation. C squared equals x squared plus y squared. Then we need to differentiate the three variable. So to differentiate the three variable, we come up with 2z dz over d. The derivative of z over dt is equals to 2x derivative of x with respect to t plus 2y derivative of y with respect to t. So since we have common 2, we'll divide both sides by 2. So since the given value is expressed in kilometer, so we need to convert the kilometer per hour into kilometer. So to convert 240 kilometer per hour into kilometer, so this is how you convert it. 240 kilometer over hour times 30 seconds. So why 30 seconds? because it is said here that the velocity after it increased 30 seconds. So since we will convert it into meter, so we need to find a value to cancel the seconds. So 1 hour over 3,600 seconds. So because in every 1 hour there is 3,600 seconds. So now you cancel the units. Then remaining is 240 times 30 seconds. So what is 240 times 30 seconds? Which is 7,200 over 3,600 kilometer. Then it is equals to 2 kilometer. So this is now the value of our adjacent, which is the x. So x is equals to 2 kilometer. So since we have now the adjacent is 2 kilometer and the opposite 1 kilometer, so we need to find the hypotenuse. So in finding hypotenuse, we use Pythagorean theorem. So we all know that our Pythagorean theorem is z squared is equals to x squared plus y squared. So we substitute the given formula to the equation. So z squared rx is equals to 2. Then ry, which is the opposite, is equals to 1. So since we have squared, we need to cancel out by putting square root here. So z is equals to square root of 5. So this is now our hypotenuse. So since we have now the hypotenuse, we write here square root of 5. Now, so we have now all the value. So we now solve the velocity. So the equation, if we go back to the equation, we have z derivative of t of z with respect to t is equals to x derivative of x with respect to t plus y derivative of y with respect to. So to solve, we must substitute the given value here. So z is equals to square root of 5 d is equals to, then our x is equals to 2 dx over plus ry 1 derivative of y with respect to dt. That's all. There's no given dy dt, so we will get dy dt is equal to 0. So here, that is square root of 5 dt is equals to, so we need to simplify it, so it will come up to 480. And we need to divide both sides by square root of 5. So it will be cancelled. So dz over dt is equals to 240.66 km per hour. So this is the velocity after it increases 30 seconds later, 214.66 km per hour.
So thank you very much for your cooperation, Mr. Professor Manito. Your answer is correct.